Hi, this is Mrs. Zukowski, and in this screencast we're going to be working on the factoring of the difference of two perfect squares. Before we get started on that, I want to just review with you FOIL, which is actually four multiplications used when multiplying a binomial times a binomial. F stands for first term times first term, O stands for outer term times outer term, I stands for inner term times inner term, and L stands for last term times last term. The little picture at the right can help you to remember what to multiply together when you're using FOIL. Now let's look at this example, 3x plus 5 times x minus 2. First term times first term, 3x times x gives us 3x squared. The outside terms, 3x times negative 2 gives us negative 6x. The inside terms, 5 times x gives us positive 5x. And last term times last term gives us negative 10. The two middle terms can be combined because they're like terms, resulting in 3x squared minus x minus 10. Now look at the example. Multiply x plus 4 times x minus 4. When I use FOIL, x times x gives me x squared. The outside terms, x times negative 4, gives me negative 4x. The inside terms, 4 times x, gives me positive 4x. And last term times last term, 4 times negative 4, gives me negative 16. The two inside terms can be combined, but when you combine those, they cancel each other out. So your final answer is x squared minus 16. Factoring can undo the FOIL multiplication. If you look at the example x squared minus 25, if we were to factor that, we would get x plus 5 times x minus 5. And if I multiplied x plus 5 times x minus 5 and using FOIL and combining like terms, I would end up with the x squared minus 25. What exactly is a perfect square? It's any number, variable, or product that can be broken into two identical factors. No radicals when you're breaking up a perfect square. Numbers that are perfect squares are simply numbers that are found when you multiply a number times itself. 1 times 1 gives you 1, 2 times 2 gives you 4, 3 times 3 gives you 9, 4 times 4 gives you 16, and so on. There's an infinite number of perfect squares, and these should look familiar to you. Variables that are raised to an even power are perfect squares. X to the second is a perfect square because x to the first times x to the first gives you x to the second. Y to the fourth is a perfect square because y squared times y squared gives you y to the fourth. Any product that has an even exponent is going to be a perfect square when you have a variable. Because remember, when you have two things that you're multiplying with the same base, you end up adding the exponents. X to the, or z to the 10th would equal z to the 5th times z to the 5th. M to the 6th would equal m to the 3rd times m to the 3rd. S to the 8th would equal s to the 4th times x to the 4th. And x to the 4th y squared is a perfect square because x squared y times x squared y would give you that for a product. Now I want you to look at these examples. Decide whether or not they're perfect squares and write down your answers. The first one, 16x to the 4th, is a perfect square because 4x squared times 4x squared equals 16x to the 4th. In the second example, it's not a perfect square. X squared is, but there's no number times itself that equals 7. In number 3, 10y to the 8th is a perfect square because 10y to the 4th times 10y to the 4th would give you that product. In the fourth example, it's not a perfect square. 64 gives you 8 times 8, but you can't break up x to the 3rd with a variable raised to the same exact power in both factors. The steps for doing the difference of two perfect squares is first we want to check and make sure that there's a subtraction sign between the two terms. Then we want to check and make sure that both of the terms are perfect squares. If both of these check, then you can continue to factor the problem. The first thing that you will do is set up your parentheses. Put in your signs, 1 plus and 1 minus, and then you will enter the factors of the perfect squares. You can check your answers with FOIL. Look at these and decide whether or not they are the difference of two perfect squares. Pause here and write your answers down. The first one, 16x to the second, is a perfect square. There's a minus sign in the middle, and 25 is also a perfect square, so the answer is yes. In the second example, 8 is not a perfect square in the 8x to the fourth, so therefore the answer to that is no. In the third example, the plus sign in the middle should be a minus, so no, the way it's written, it's not a perfect difference of perfect squares. Number 4, 121 minus x to the fourth is because 121 is a perfect square, x to the fourth is a perfect square, and there's a minus sign in the middle. Number 5 is not the difference of two perfect squares because of the 12. And number 6, m to the sixth minus 49 is perfect, the difference of perfect squares. The first one that was the difference of perfect squares, we're going to actually factor. 16x to the second minus 25. So I set up my parentheses and I put in 1 plus and 1 minus. Then I break up 16x to the fourth with 4x and 4x, and I break up the 25 into 5 and 5. I could have also written this answer as 4x minus 5 times the quantity 4x plus 5. Try factoring 121 minus x to the fourth by yourself. After you put your two parentheses, you put in the plus and minus sign. 121 breaks up into 11 times 11, and the x to the fourth breaks up into x squared times x squared. You can check this answer using FOIL. Factor m to the sixth minus 49. This problem requires two parentheses. Put in the plus and minus sign. M to the sixth breaks up into m to the third times m to the third, and 49 factors into 7 times 7, resulting in the answers in the parentheses. Some expressions can be factored more than once. Factor completely the expression 18x to the fourth minus 50. Start by looking for a greatest common factor to factor out. The first step is to factor out a 2 because both of the terms have that in common. After I factor out a 2, in the parentheses I have 9x to the fourth minus 25. 9x to the fourth minus 25 is the difference of two perfect squares, and I'm putting two parentheses to factor that. When I do that, I'm putting in 1 plus and 1 minus. 9x to the fourth gets factored into 3x squared times 3x squared, and the 25 gives you 5 times 5. Don't forget that the 2 is still one of your factors, so in the end you have 3 factors. The 2, in parentheses, the 3x squared plus 5, and then the 3x squared minus 5 in the second parentheses. Try to factor x to the fourth minus 81 completely. X to the fourth minus 81 is the difference of two perfect squares. So I set up the parentheses, put in my plus and minus sign. X to the fourth I break up as x squared, and 81 becomes 9 and 9. So I have x squared plus 9 times the quantity x squared minus 9. Can this be factored more? X squared minus 9 is the difference of two perfect squares, so that can be broken up further into x plus 3 times x minus 3. Make sure you don't factor x squared plus 9. The sum of two perfect squares is not factorable. Factor the following problem completely. 12x to the fourth minus 27. The first thing we can do is take out the common factor 3, resulting in 4x to the fourth minus 9 in the parentheses, which is the difference of two perfect squares. So the final answer is the 3, and then in the two parentheses you have 2x squared plus 3 times 2x squared minus 3. Factor x to the 16th minus 1 completely. If you do this correctly, you should have several factors at the end of your problem. X to the 16th minus 1 can be factored as the difference of two perfect squares. The x to the 8th minus 1 can be factored again. The x to the 4th minus 1 can be factored again, resulting in 4 factors total. And the x squared minus 1 can be factored one more time, resulting in 5 different factors that the product is equal to x to the 16th minus 1. Thank you for watching.